Yeah, okay. So welcome back, everybody, from the coffee break. And let's start the last session of today. The first speaker of the session is Matthew Leighton, and he's going to talk about dynamic and thermodynamic bounds for collective motor-driven transport. You have 10 minutes. I will let you know 2 minutes before the end of your talk. And yeah, thank you very much. The floor is yours.
Great. Hi, everyone. Thanks for giving me the opportunity to speak here today. I'd like to tell you about some work done by myself and my supervisor, David Svok, on performance bounds for collective motor-driven transport. So within cells and biological organisms, important molecular cargo are transported by motor proteins like kinesin and myosin. And my favorite feature of these motors is that they work collectively with widely varying numbers of motors attached to individual cargo working together to move them. So to give you some examples of these kinds of motor numbers, for kinesin pulling small vesicles, you might find on the order of 1 to 10 motor proteins per cargo. For myosin motors sliding actin filaments within muscle tissue, you might find on the order of 100 motor proteins. And for kinesin pulling large organelles like mitochondria within cells, experiments have found over 200 motor proteins attached to a single mitochondria. So the question we set out to answer in this work is, suppose you have a kind of collection of these individual components that make up a collective transport system. So some motors, a cargo, and you want to design a system that's as performant as it performs as well as it possibly can. What is the best way? How can you hook them up? Are there any fundamental limits that constrain the performance of these systems, regardless of how you connect all these different components? So to think about that, we can consider kind of a very general model for these kinds of systems where we have a single diffusive cargo coupled to an arbitrary number n of motor proteins walking along some substrate in one dimension. We can characterize each motor by some bare diffusivity, di, as well as chemical driving force, fi. And now all these different components are coupled together in general by some conservative potential, which can in general include terms for things like coupling between the motors and cargoes, interactions between the motors, as well as periodic energy landscapes for each of the motors. As an example, you might find something like this, where motors experience both metastable states, energy barriers, and other features like that. Finally, we assume that all the components of this system evolve according to multipartite overdamped Langevin dynamics. And for multipartite dynamics, we can write down an expression for the total entropy production rate by this system as a sum of terms due to the entropy productions of each component comprising the collective system. And in particular, these terms have ensemble averages of the local mean velocity squared, which is related to the probability flux. And when written in this form, the kind of cool thing you can do to this entropy production expression that we realized is use Ensign's inequality, which constrains, relates the average of a square of a function to the square of the average of a function. And applying Ensign's inequality to this expression for the entropy production, we can derive what we call the Ensign lower bound on the entropy production rate. So here we have the total rate of entropy production by the collective transport system bounded by the square of the mean velocity divided by what we're calling the bare collective diffusivity of the system. So this is a quantity that depends only on properties of individual components. In fact, it's a reciprocal of a sum of reciprocals of all the diffusion coefficients of each of the motors and cargo. And this form might look very familiar to you because it is in fact analogous bound to the thermodynamic uncertainty relation, which can be written in the same form, simply replacing the bare collective diffusivity with the effective diffusivity of, for example, the cargo, or indeed any number of these components. And what's really cool here is that the Ensign bound and the thermodynamic uncertainty relation give you two lower bounds on the entropy production of this system that have similar forms, but in fact, either one can be tighter in different circumstances. So in fact, even for a single Brownian particle in like a tilted washboard potential, either the bare collective diffusivity or the effective diffusivity can be larger, making either of these bounds tighter. So from the Ensign bound, we can derive a set of performance bounds constraining individual performance metrics of the system. For example, We derive an upper bound on the mean velocity in terms of the bare collective diffusivity and the sum of the chemical driving forces. We can also derive an upper bound on the Stokes efficiency, which is kind of like the ratio of work against viscous drag to the amount of chemical energy consumed by the system. And this might look familiar because it's very similar to an analogous bound derived from the TUR in 2016, again, replacing the bare collective diffusivity with the effective diffusivity. And I'll remind you again that either of these can be tighter or looser depending on the setting of the system. Finally, by combining the Ensign bound and the TUR, we can also derive a lower bound on the coefficient of variation, which is the ratio of the standard deviation to the mean of the amount of forward progress by the cargo in a given amount of time. What I want to stress here is that the bounds we've derived using the Ensign bound are all independent of how all these different components of the system are coupled together. So they only depend on properties of the bare subsystems in isolation. When motors are identical, which is often the case in real biological systems, so with identical driving forces and bare diffusivities, but in theory still coupled to each other in the cargo in different ways, we can also derive a couple of Pareto frontiers, which constrain combinations of two different performance metrics for the system. So for example, we get an upper bound on the sum of the Stokes efficiency and normalized velocity, as well as an alternative Pareto frontier constraining combinations of chemical power consumption by the collection of motors and velocity. So to explore some of these bounds and kind of get an idea of what conditions lead to their saturation, we can consider a specific simple example system here. So in particular, we consider two identical motors with identical driving forces, Fchem. We give both motors a sinusoidal periodic energy landscape with a maximum force Fmax, which you can think of as kind of proportional to the barrier height of the energy barriers between metastable states, periodicity L. The motors are quadratically coupled to the cargo, and we assume no interactions between the motors. So this figure on the right here gives you an example of the kind of trajectories that you get out of this model, where here the light curves denote the positions of the motors over time, and dark curves denote the cargo. And as we vary the parameter Fmax over Fchem, which I'll remind you is kind of analogous to the barrier height of energy barriers between metastable states, we see that as Fmax increases, the system looks more and more like it's taking discrete steps. So really with this very simple model, we can simulate kind of a wide range of different kind of types of motor dynamics. And just as an aside here, we've done some rough calculations, and for kinesin 1, it seems like this ratio is on the order of 0.4 to 0.8, so kind of the green or orange curves in this figure.
You have two more minutes.
Yes, thanks. So we can explore the Pareto frontiers we've predicted using this model. So these curves here show performance trade-off curves between Stokes efficiency and mean velocity. And what we find is that the Pareto frontiers, and in general, all the bounds we've predicted, are exactly saturated when Fmax equals 0. So when there's no, when the periodic energy landscape of the motors is totally flattened. And as that landscape gets more rough or bumpy, energy barriers decrease, the performance trade-off curves get farther and farther from the Pareto frontier. We see the same thing with the other Pareto frontier as shown here. And lastly, I just want to show a brief comparison with some experimental data from this paper by Purcell et al. Showing thermodynamic efficiency, so work done pulling a cargo against a external force versus velocity for myosin motors from a variety of animal muscle tissues. And we can show that our predictions predict a similar analogous Pareto frontier to what we derived for Stokes efficiency for the thermodynamic efficiency when an external force is present. And we see that these experimental results are consistent with our Pareto frontier for a maximum myosin velocity of about 12 micrometers per second. And interestingly, these experimental data points seem to get pretty close, but don't quite reach the Pareto frontier we predict. So to summarize, we've derived a Gensen lower bound on the entropy production rate for a collective transport system that holds quite generally. This implies new bounds on velocity, efficiency, and precision, which are important performance metrics for these systems. Likewise, when you have identical motors, these results imply several Pareto frontiers constraining combinations of performance metrics and implying performance trade-offs that these systems have to contend with. For a simple model, we show exactly the conditions where these bounds are saturated. And our findings seem to be consistent with experimental results from myosin motors. So with that, I'll thank everyone who helped to fund this work, as well as everyone in the Savak group, and especially my supervisor, David. And I'll leave the archive link here if anyone's interested in learning more about this. So thanks so much for listening, and happy to answer any questions.